Hi everyone, welcome to another episode of Power BI Virtual Chapter. My name is Julie Cosmano. I am the co-chapter leader of Power BI Virtual Chapter. Firstly, I'd like to thank our sponsor, Pragmatic Works, for sponsoring our virtual chapters. They're the reasons why we could give away some prizes, and this time around we're also actually giving away a $25 Amazon gift card. So if you fill in the survey towards the end of the session, you'll be entered into a prize giveaway there. Okay, so guess what? It's December already, and it's just been a month after Past Summit 2014. So I'm really excited to be back here actively hosting of the Past BI virtual chapters. And obviously, you may already know that there are several virtual chapters out there, and the numbers are growing. So if you are really into other parts of SQL Server or data in general, just outside BI, don't forget to check them out. So go to sqlpass.org. That's where you get more information for the other virtual chapters. Now I'd like to highlight a number of virtual chapter meetings that I hosted for the month, the last month of this year actually. We actually do have another session for business intelligence virtual chapter. So check that out with Mickey Stewie, and more information will be displayed later in this slide deck. And I'd like to also mention that there is Past Business Analytics Conference in 2015. It's on April 20th to 22nd in Santa Clara, California, and I believe they have announced a number of the speakers already. So check it out. If you're really into the business analytics side, this is, I think, a good conference to go to. And okay, so this is going to be a bit of a self-shameless plug in a way, because I'm one of the organizers of SQL Saturday Melbourne. We do have SQL Saturday Melbourne in Australia on 7th of February 2015, and we do also have 3 exciting pre-con sessions. One of them is on execution plan by Paul White, and then we also have Power BI with Peter de Braak from Netherlands. Actually, he's coming to Melbourne, so that's going to be exciting. And we also have a BIML session with a number of speakers, and I think there's also a DB element on that too in terms of managing BI service and things like that. So check it out if you are actually local or willing to travel to Melbourne. We would like to invite you to come to SQL Saturday Melbourne. All right, so for volunteering, if you're interested, don't forget to sign up at volunteer.sqlpass.org. And then we do also recognize outstanding past volunteer, and the highest award is actually Passion Award winner. And yeah, so if you have a chance, please nominate someone, because it's nice to be recognized. And if you'd like to stay involved, go to sqlpass.org for more information, and go to or follow the Twitter account sqlpass. And we also have BI virtual chapter website too, which is bi.sqlpass.org. And this page is a little bit outdated actually. We do now have 40 hours of free learning available on our YouTube channel, on our Past BI VC YouTube channel. And this session will also be recorded and will be posted there too. As I mentioned before, please fill in the survey at the end of the session. Please give a constructive feedback for the speakers or for the speaker today, and also for the virtual chapter in general. And upcoming session is with Mickey Stewie on the 18th of December 2014, and that's actually 1 p.m. Sydney time, which is equivalent to 6 p.m. LA time or PST time. I think this is a great one to go to. She actually presented this at Past Summit, so yeah, so if you could join us, that would be great. Now, without further ado, Kevin Asgarth will actually be presenting implementing data warehouse patterns with the Microsoft BI tools. So this is one of my favorite subjects. And let me just get the controller to Kevin, if you bear with me for a moment. Okay, Kevin, I think you have the control now. I can see your screen.
Okay, great, thank you. First of all,
I can't hear you.
Can you hear me okay, and you can see my screen okay? Okay, great. Most important things for the day. So thank you everyone for coming. Happy holidays, everyone. As Julie said, hard to believe it's December already. And today's topic For people who've seen my presentations before, but usually do presentations in the 13-tip Baker's Dozen format, today's topic is 13 productivity tips for implementing data warehouse patterns using the SQL Server and BI tools. Nice long title. My name is Kevin Goff. I'm a SQL Server MVP. Just a very quick bio on me, and then we'll get started. I've been in the industry since 1987, live in central Pennsylvania and speak usually in the Mid-Atlantic area, different community events, and also the SQL Live 360 conference brand. My email address, if you want to send me an email with any questions, is kgoff@kevinsgoff.net. I'm also on Twitter. Twitter handle is just Kevin S. Goff, and my website, very important here because that actually has the download for the slide deck, is www.kevinsgoff.net. Actually, just to show that the slide deck is indeed out there, if I go to my website here real quick, and on the right-hand side, go to the download area. On the download page, the second one down here is the slide deck that corresponds to today's presentation. Don't be fooled by the date of 11/14, actually updated for today. Also, feel free to browse for any other downloads or webcasts I've got up on my site. I've got different downloads for different SQL and business intelligence topics. Also, some webcasts, either links to ones I've done here for past or webcasts I've done on my own. So feel free to go up on my site and pull down anything that might interest you. And again, if you have any questions, my email address is kgoff@kevinsgoff.net. Also, because we have an hour and because I've got a lot of material to cover, what I usually try to do with questions is take care of them at the end. I usually try to give detailed answers, and so I prefer to do that after the presentation is over. So any questions that are in the queue that Julie will take care of and manage in the queue, I'll go through and answer them at the end. Or if you simply want to email me with questions afterwards, that's certainly great as well. So the overview, the objectives for today, obviously the topic is data warehousing patterns with the SQL Server and BI tools. Well, if you've been in data warehousing at all, or if you've read about data warehousing, or if you've been living it for any period of time, it's a little bit like running a medical practice or a legal practice, except you might not necessarily get paid as much as a doctor, but certainly the patterns, the methodologies involving data warehousing certainly remind me, because I have some knowledge of medical practices in particular. It's almost like running a medical practice. There's some recommended practices, many tried and true methodologies, many patterns, and also anti-patterns we're going to talk about today. So certainly some overlap between the two. Now, this presentation is actually based upon some custom courseware that I wrote back in a prior lifetime. It's packed with a lot of details. They're going to help long after this presentation is over with. The goal of the slide deck here, I actually have about 60 slides with a lot of detailed information. The goal is to give people something to use long after this 60-minute presentation is over with. Now, I actually wrote an article for Code Magazine. I've been writing for Code Magazine for a number of years, and I've got the link here. This presentation is actually based in part on an article I wrote a little over a year and a half ago, if you want to pull down the link. And also, if you are not already familiar with this book, I highly recommend that you go out, read this, read it again, and read it again. I'm actually not exaggerating when I say this. And that's the Data Warehouse Toolkit, the Complete Guide to Dimensional Modeling by Ralph Kimball. Most people probably, if they have been involved in data warehousing at all, are familiar with at least the name Ralph Kimball, if not the methodology. One of the great things about this book is that it's not about a technology per se. This book was written back in the 2002-2003 time period. Even though there have been updates since, about 98–99% of what was written back in 2002 in this book is still applicable today, because it's not about SQL Server or Oracle or any other type of database. It's actually on methodologies for building data warehouses. And so as a result, it's much more timeless than, say, a book on a particular technology that might become obsolete after a few years. So I highly recommend going out and getting it. Also, I have links in the slide deck to if you want to go pick it up on Amazon, as well as a link to the Ralph Kimball the Kimball Group website. A lot of design patterns, a lot of tips for implementing the Kimball methodology up on that Kimball Group website. So highly recommend spending some time on that material. Well, some of the concepts we're going to cover today. If you work in data warehousing enough, you hear terms that get used over and over again. And some of the things we're going to talk about here, but perhaps multiple times, we're going to talk about things like granularity and transaction grain. And if you're not familiar with those terms, if you're not quite sure, that's why we're having this presentation. Also going to talk about conformed and common dimensionality. When we have data that's associated with multiple business processes, we might have some commonality, and we might look at different processes like budgeting and also sales by a common dimension, maybe a business product or a time period. Also going to look at role-playing dimensions. Role-playing dimensions are a certain way that the data tends to be related. You can have one piece of information that might serve multiple purposes or multiple roles across tables. You'll look at hierarchies. Hierarchies are something that you are going to see in almost any data warehouse. You're going to have at least a few examples of parent-child relationships that reflect the way business users might want to roll up or drill down on data. Going to take a look at fact dimension usage. Now, if you're sort of familiar with what a fact table is, but not quite, again, that's why we're here. I'm going to talk about the different types of fact tables that exist. There are transaction tables, there are snapshot tables, and there's a term that almost seems to be a contradiction in terms, factless fact tables. Going to look at different types of dimension and dimension relationships, like junk dimensions, star and snowflake schemas, and a special type of a dimension, not one that's terribly common, but one that we need to be aware of, called a dimension outrigger. Now, we're covering patterns here in this presentation. So an example that I might use with one particular pattern, you could apply to 5 different types of businesses where all the data might be different, but the pattern, the characteristics might be the same. We're going to also talk about a topic that is usually present in many data warehouses, and that's what's called slowly changing dimensions. This is a topic that we could spend an entire hour just on that topic. And related to that is another characteristic called early and late arriving data. When we have slowly changing dimensions where data changes over time and we care about tracking those changes, well, the changes occur based upon a particular point in time. Well, sometimes we get those changes early, and sometimes we get them after the fact. And so depending upon when we get the data, well, we might have some corrections or some additional processing that we have to implement. So in the standard Baker's Dozen 13-tip format, here are the actual 13 tips that we're going to take a look at today. Now, they're actually broken up into a couple of sections. First of all, going to take a look at the goals and major components of a data warehouse or an analytic database. Then we're going to take a look at the different types of fact tables that we have available to us in data warehousing. Then we're going to take a look at dimension tables and also how they relate to fact tables. In some scenarios, relationships between dimension and fact tables are very simple, and other times they're a little bit more complex, reflecting the different relationships that we have with the available data. So we're going to take a look at a couple of different patterns there. Some of these are fairly simple, like role-playing dimensions and even junk dimensions are not all that complicated. But then we get into things like bridge table relationships and type 2 changing dimensions. Well, there we need to stop and talk a little bit more about some of the specifics and some of the things that can happen. Well, a minute ago I said that just in the same way that you have patterns in data warehousing, you also have some anti-patterns. Well, I'm going to talk about 2 in particular, 2 that to this day I see, as a matter of fact, with a particular client, saw one of these just the other day. So we're going to take a look at some of the absolute don'ts in data warehousing, and 2 of them in particular are the dealing of null values and also the storing of ratios in fact tables. So those are the topics we have for today. Now, just as a starting point for data warehouses, If you're brand new to data warehousing, the thing to keep in mind is that a data warehouse, in one respect, is no different than a relational normalized database in that it's just simply another database and I'm using SQL Server in particular as an example here, although it could be Oracle just as well. So in the same way that you connect a SQL Server to connect to your transaction databases and some of your historical databases and your reporting databases, you might also have a database, probably on a separate server, that's holding your data warehouse or a series of data marts. So in that case, you could say that it's just another database. However, the patterns that go into, and the methodologies that go into the structuring of the data and how we populate it are very different than your standard OLTP relational normalized database. Data warehouses and data marts tend to be denormalized and flat, as opposed to your transaction databases, your OLTP databases, which are generally normalized and in many cases might go all the way up to third normal form. Well, for people who are new to data warehousing, that in itself is almost a culture shock, because you wonder why. Why is it that after all that I've learned about OLTP and about normalization, why would you turn around and in a data warehouse denormalize everything? Well, we need to stop and think about some of the reasons why OLTP databases are normalized, and where some of the priorities and some of the major points in an OLTP system might be different than they are in a data warehouse. In a transaction system, we're interested in getting data into the database as efficiently as possible, and clearly we're also interested in implementing the types of relational constraints, relational integrity checks to make sure that that we don't have any violations of our normalization form. But certainly one of the big goals is getting data into the database as efficiently as possible. Well, in a data warehouse, in a data mart, where we have the one historical version of the truth and we want people to be going there for all sorts of historical reporting and analysis, the goals tend to be a little bit different. We're more interested in what's the most efficient way to get data out of the system. That's really not to say that we're not interested in efficiencies in getting data in, but typically the processes to populate a data warehouse, there's typically just one much smaller set of ETL processes as opposed to an OLTP system that could be hit by thousands or hundreds of thousands or millions of users. So the emphasis there tends to be a little bit different. And so a key process in data warehousing is what we call shaping data into fact dimension models, taking data from our transaction systems, from our historical systems, from our legacy systems, and shaping them into fact dimension structures. Because when we do that, once we get data into fact dimension structures, typically more denormalized and flat, there are a lot of different reporting tools, business intelligence tools, analytic tools that can really take advantage of denormalized structures to get data out as efficiently as possible, and even make it possible for power users or end users to get at data without necessarily knowing how to write queries. So certainly the emphasis coming into a data warehouse is going to be very, very different. Now, one of the clients that I have is a steel manufacturer, and you could certainly fill in a lot of the nouns and the verbs here with data from different clients that are out there that you might have. But one of my clients is a steel manufacturer. Now, at the end of the day, they have people who want to look at things like order tons, production tons. They want to look at roll-ups of those over periods of time. They want to look at defects. They want to look at regrades. Material might need to be regraded, and even though that's something we want to minimize, it's a fact of life. Well, we might want to know the percentage with respect to thresholds. We might have a threshold where we don't want regrades to be more than maybe 3% of production. We want to look at quality test results. We want to look at heat chemistries. Well, if you're in, say, the medical world, you might want to look at tallies of patients that have come through a clinic, or tallies of patients with this particular diagnosis code. And we could go to another industry and take a look at a completely different set of metrics that people want to roll up data. Well, there's also a magic word in the data warehousing world, and it's one that Ralph Kimball mentions several times in his book, and that magic word is the word buy. If you ask business users, what are your business dimensions? What are your dimension attributes? Well, they might look at you like you're a little bit crazy. They might not understand that term. But then if you ask people, all right, how do you look at data by? That magic word by just opens up all sorts of light bulbs, all sorts of possibilities for the different business entities by which people want to look at data. For instance, we might want to look at orders by customer, by order number, by material type, by material name, by responsible department, by defect type, by time period. There's that word by over and over and over again. Well, the data at the top here represents our facts, our measures, the things that we want to measure, the things that we want to roll up. The data down at the bottom represents our dimension attributes. Now, loosely speaking, those dimension attributes, they reflect the master tables that you might have in a transaction system. So there's going to be some method to take entities that you might have in business master tables and get them over to business dimensions. So that is an end game of this particular customer. Now, as far as how you physically might implement it, well, there are different approaches that you might have available. Some people might go the whole 9 yards and build a data warehouse or a set of data marts and then build some OLAP cubes using something like analysis services, which can offer some very, very advanced analytic capabilities. Or some people might structure data in fact dimension structures in just a relational data warehouse in a denormalized fashion, and then use some of the self-service tools, self-service BI tools that are like Power Pivot and Power View for power users to get at the data. So there's no one absolute path as far as what technologies you're going to use within the Microsoft realm to satisfy these requirements. There's certainly different possibilities, and the technologies that a company might be using in an environment are going to drive what the end result might be. Now, there's obviously going to be a lot of discovery that goes into identifying all these different requirements. I've obviously just highly summarized these here. Some of the requirements might come from existing legacy reports that people want to automate or improve. Sometimes the discovery might go through a lot of talking with the different business groups within the company. So that discovery process can be lengthy in itself. But at the end of the day, we need to identify a set of metrics that we want to roll up, and then by what business dimensions. Now, I'm going to jump over to the sort of the other side of the world. One of our end goals, by the time it's all said and done, is a usage area of where the facts and dimensions come together. Now, I'm actually going to skip forward one slide to a simpler one and then come back to the previous one. It's just a second here. A particular data mart that we might have for someone in the healthcare area. Well, we might be taking a look at tallies by diagnosis code visit, by procedural code visit, by quality indicator. There might be several different types of visits that occur. And we might want to roll up the data by different business dimensions that are available to us. Well, notice how we have a patient dimension that's common across nearly every different business process. In the healthcare world, certainly almost every business process is going to involve the patient identifier. But then we have things like physicians, where the physicians might come into play with some of these, but not necessarily all of them. And then we have maybe some more specialized dimensions, like for instance, we have a room. We might track when patients go from one room to another within a large medical facility. Well, that room might not have any relevance to other business processes, but it might to that particular business process. So any data warehousing endeavor that we go into, whether it's something in the medical world or now hopping back one screen, something in the manufacturing and the production area. Well, in the production area or in the manufacturing area, we might have orders, we might have material production, we might have defects, we might have reworks, and then we have the different business dimensions that intersect with those processes. So on the customer order side, we might track orders by order number, by order promise date, but we wouldn't by chemical element, because maybe chemical element has no tie to a customer order. That's not a bad thing. It just simply means that some dimensions are tied to some business processes, which ultimately becomes a fact table, but not necessarily other ones. So we're always going to have these dead areas where some dimensions don't relate to certain fact tables. Now, as we're going to see, some of these relationships are going to be very simple. For instance, we have orders by customer order number. Well, that's pretty simple. But other times the relationships are going to be more complicated. For instance, we might have material production by responsible unit area. Well, this might be a many-to-many relationship involving a bridge table. So the point is that some of these relationships are going to be simple and some of them are going to be more complicated. Well, some of the end results that the people are looking to get at, that are identified either from legacy reports that the people are looking to implement and maybe improve on in a new data warehouse or maybe new analytics. Every picture, every type of analytic that someone wants to get at. You know that old line about a picture being worth 1,000 words if it's the right words. Well, every one of these represents some different business activity or activities, plural, that we might want to look at by different dimensions. Now, you can obviously pull down the slide deck and go through these examples. I'm not going to spend a lot of time with any one of these, but we might want to take a look at regrade percentages over a period of time by responsible unit. Well, if you notice, if you're familiar with PowerView in some of the newer BI tools that come from Microsoft, PowerView gives the capability to take a look at different plotted observation points over a period of time and even have a play axis. So we obviously would need to structure some type of data warehouse to take a look at regrade percentages over time by time period and by department. Well, another requirement that we might have is to take a look at tonnage by department or maybe by first-time regrade. There's that magic word by again. Every time someone says the word by, there's an underlying dimension attribute that we need to account for and structure for in the data warehouse. We might also want to take a look at percentages over a period of time. So we've got a chart here that's reading from a data warehouse that takes a look at regrade percentages and also regrade tons. Now, something that I'm going to bring up a little bit later is that percentages are things that we want to calculate on the fly, whereas numbers like tons and order dollars and things like that are ones that we want to store in a data warehouse. Percentages are the things that we're going to want to calculate on the fly. We're usually not going to want to store them. I'll explain a little bit later why I'm saying that. Now, when we think of data warehouses, we oftentimes think of rolling up dollar amounts and rolling up profit and rolling up revenue and things like that. But something to keep in mind is that we oftentimes might also want to roll up tallies, roll up instances where dimension member values come together to form an event. We might have a factless fact table, sort of a contradiction in terms almost. We have a factless fact table that gives us nothing more than tallies of defects or a number of times that people have visited a doctor or something like that. It might not seem as glamorous, but in some analytic environments it might be just as important as any other type of measure. Well, another type of analytic requirement, kind of a more specialized one, we might want to take a look at a scatter chart and even calculate things like correlation coefficients or regression trend line slope calculation, where we plot two pieces of information, the customer count by city against revenue. Well, once again, we've got to account for revenue, we've got to account for customer counts and cities within the data warehouse, and when that's structured in fact dimension models, things like this in Excel are become possible. We might also take a look at production tons, not just by department or by unit, but also by specific weeks. So in addition to storing things like days and weeks and months and years in a date dimension, we might also store things like week numbers, because we might want to break out production tons by next week and the week after that and the 3 weeks in the future and so forth. So again, every one of these means there's some kind of corresponding analytic requirement, which means there's some type of corresponding data that we've got to account for in the data warehouse. Now, one thing to keep in mind about data warehouses is that they're not just for rolling up data. Sometimes we tend to think of data warehouses for rolling up data by region or by product brand to get at some very high numbers. That's certainly true. That's an important part of it. But data warehouses are also for drilling down into more detailed information. That's something that we really need to keep in mind, is that not only do people want to roll up data, many of your information workers are going to want to drill down in information. So we need to be able to store and to take into account data down at the lowest level, whether it's the product SKU or a transaction ID, and even provide the capability in different analytic tools to implement drill-through actions, so that if I'm taking a look at a particular production amount and I want to know all the IDs that make up a particular number, well, we need to account for that in the data warehouse, and so that means that end users in something like Excel can have drill-through actions to get down and take a look at data down at the lowest level. Now, how you might go about doing that is going to obviously vary depending upon the data, but the point is that data warehouses are not just for rolling up data. We need to make sure to account for data down at a very low level, because sometimes drill down is going to be just as important as rolling up. Now, let's take a look at this more from an actual fact dimension structure. Very basic example here of a fact table with two dimensions. We have customer orders by date and by customer order dimension. Now, fact tables represent, again, what happened. That's our business activity, whether it's sales transactions, forecasting transactions, whatever the business activity happens to be. And then the business dimensions provide the business context to the fact tables. They are, loosely speaking, the business master tables. So a very simple example of relationship here. We have a fact customer order table that's tied to a customer order dimension by order number, and to a date dimension by a foreign key that's tied into a primary key and a date dimension. And I'm going to ignore these other measures here. We might want to simply roll up order pounds and order tons. Now, some people might only store the order pounds and then calculate the tons on the fly by dividing by 2,000 or whatever, or sometimes people might actually store both. Now, most data warehouses are going to have many fact tables and a larger number of dimensions. It's obviously best, if you're starting this from scratch, to prototype with a couple to get the hang of the pattern. Now, this is a very, very simple relationship model. Sometimes relationships between facts and dimensions are very simple, and other times they're going to be more complicated. Now, as I'm going to show in just a few minutes, the primary key, foreign key relationships and the columns themselves ideally should be based upon 4-byte integers. Now, in some instances, you might use the small int, the short int, or a tiny int if you have a very, very small number of dimension members, far less than 255. But for many, many fact dimension relationships, you're going to see integer values used as surrogate keys between the two tables. Now, as I said, relationships can be a little bit more complicated from time to time. One example is what we call a role-playing relationship. I'm going to talk about this a couple of times here. For instance, in this fact material table, I've got two foreign key relationships into the date dimension, based upon production date and based upon promise date. We might want to take a look at production based upon when it occurred, and we also might want to roll up the production based upon when was it promised, because it might have been a different date. The date is serving multiple purposes within this fact table. And so we call this a role-playing relationship. You typically see this with dates. You can have it with any type of dimension, but you typically see it with dates. Now, other types of relationships that you might see, you might have what we call a self-join relationship. You usually see this with organizational hierarchies, like sales hierarchies, where one salesperson might report up to another salesperson, and another salesperson might report up to yet another salesperson. So sometimes we have self-join relationships, usually with organizational hierarchies. And as I mentioned a few minutes ago, we might have factless fact tables where we don't actually have any numbers per se that we roll up. They're just simply an intersection of the different dimensions that come together to form an event, how many times something happened. So we might have a table of defects where we simply want to know the tally of how many defects occurred based upon customer order, or based upon the piece of material or any item related to the piece of material, or by responsible unit. So again, factless fact tables can be very, very important for different data warehouses. Now, not all numbers, when we have them in fact tables, are going to be summed. Coming back a minute ago, within fact material, we want to roll up production tons. And within fact order, we want to roll up order tons. Well, sometimes the numbers in here are ones where we want to aggregate, but not based upon a sum. For instance, if we're storing things like heat chemistries, well, we might want to know over a period of time not what's the sum of chemistries, because those temperatures wouldn't make any sense, but maybe an aggregation, maybe a maximum or a minimum or an average. So not just because we have a fact table doesn't necessarily mean that we're going to sum the numbers. There might be other aggregation methods we might use. Now, as far as storing percentages, again, we're going to talk about them later. Typically, we don't want to store percentages in fact tables. We want to drive them on the fly, and I'll explain why. Now, many people are of the opinion that, initial opinion, that fact tables are going to have millions of rows or larger. Well, often, but not always. Fact tables might store things like thresholds or goals. For instance, we might have regrade targets. Regrades or defects are fact of life, but we don't want their percentages to be above a certain amount for any time period and based upon a particular unit. So we might actually store KPI goals or thresholds or sales goals in fact tables, even though those tables are going to be smaller by comparison. So there's nothing that says a fact table has to have millions of rows. They could possibly be smaller. Now, coming back to the different types of requirements we might have, I mentioned that people sometimes want to roll up and to drill down. Well, that implies hierarchies, parent-child relationships. And here's one example. In this particular chart, we're taking a look at sales over a period of time by month. And we've also got a line chart here with markers to show the sales by month for any one product with respect to its parent. I'm actually using the AdventureWorks example here using road bikes. And I'm taking a look at it for the months of 2007. Well, here in April, we had so much in sales, and road bikes were a certain percent of whatever the parent happened to be, in this case, bikes as a whole. And we actually noticed that in some months, the percentage of parent might go down, even though the sales might not necessarily change. There might not always be a direct relationship, a direct correlation between sales in any one month and the percent of parent, because maybe other products within that category or brand might be performing better or possibly worse. Many times in brand management, analysts might want to know how something is doing with respect to other products or other items within a brand. And so storing those relationships of what products roll up into what categories or subcategories or whatever is going to be very important. So once again, we have a chart that's reflecting some type of requirement we need to take account for back in the data warehouse. Now, you could almost have a separate conversation. I mentioned KPIs a minute ago. You almost have a separate conversation about KPIs and the different things that people might want to do in performance scoreboards. Well, certainly to have a KPI implement a scoreboard and a scorecard means that we need to account for the KPI and the goal and the rules back in the data warehouse in some way. If we want to be able to take a look at time periods by product or by whatever and see that something is high or low with respect to a goal, and then be able to break it down further by something like city or whatever dimensions are available to us, once again, we need to be accounting for those back in the data warehouse as well. Sales by person, not only for the current time period, but also for time period a year ago. We might have KPIs not simply just for now, but for maybe 1 year ago, 6 months ago, whatever the analytic requirements might possibly be. And so we might have rules for our KPI both for now and for, say, a year ago, because we might see that Jose here is at 80% of his target. Well, that's pretty good, or that's okay. But a year ago, he was at 85% of his target, so he's actually trending downward. So again, these types of metrics are things that we might need to store in our fact tables. Now, I'm going to take a look at this from a completely different realm, and now we're going to start to drill down into a little bit more specific information. Every data warehouse has a story. A data warehouse is is really the reflection. The data is a reflection of the collection of different data for different processes, different activities along different business grains. And so there's a story to tell. And every organization should have this. Now, I've had many spirited debates with clients, with different coworkers about putting something like this together. You know, sometimes people think, you know, it's all in our heads. We know how these processes work, so why should we put them down on paper? Well, this process can still be very enlightening to maybe capture some data requirements that maybe aren't necessarily obvious. Many years ago, I worked in the food industry, and so some of my clients, companies I work with, were companies like Keebler and Land O'Lakes and Tyson. Well, all their data might have been different, but their patterns were still the same. At corporate, they had internal order entry, and they had demand management, and they had invoicing, and the level of granularity for the data at corporate might have been by invoice number and date and ship account and product SKU, because that was the information that they were shipping to the distribution centers that would ultimately get the food products into the retail area. But that's only part of the picture. When you're in the food industry, you're typically implementing budgets or forecasting information. Well, budgets might be implemented by region managers or some type of higher level manager, and they're going to budget in cases. And they might budget by region or by market or by product brand, and they might do it by quarter. And then we might have a cost of goods fee because we ultimately want to calculate profitability. Well, that cost of goods fee might come in monthly, and the level of granularity might be the product group. And then we have sales brokers who are responsible for working with the retailer to make sure that, and the manufacturer to make sure that the right products get into the retail area at the right time. So those field sales brokers are working with the retailers and working with other people in this process, and they're dealing with data at the bill to account level and the product SKU or the product subgroup and time period, so that we can make sure that we get plenty of butter into in the retail area by Christmas and by other periods of time where, you know, people tend to buy more butter. Well, that's still not the entire picture. Remember that the manufacturer, at the end of the day, they want to be able to implement full, complete reporting that shows what did we ship, what did we sell, what was our profitability, what happened at retail. Well, there's still a missing picture here, and that's what actually happened at retail. Well, when data or when products actually get pushed into the retail cycle, that data is usually owned by, in the old days it was cash register data. These days it's scanner data, and that information is usually held by the syndicated suppliers. Companies like IRI, AC Nielsen are two of the top ones, and they're more than happy to turn around and sell the data at point of sale back to the manufacturer for a pretty good price, and that data is in consumer units. And it might be store-level data or retail account data, and by UPC code. Well, you can probably see where we're going here. This big picture shows us that we've got some basic requirements from the get-go. We need conversion factors to go back and forth from pounds to cases and cases to units. We need mapping tables to go from UPC code to product SKU. We need relationship tables to relate ship to accounts to bill to accounts to markets and stores. We need to be able to deal with data at different levels of granularity, and we also need to account for change. If you've worked in this particular industry, you know that you can have reorganizations. So one particular chain might be associated with a certain set of stores at one point, and then a reorg might occur, and we might need to account for data under the old reorg structure and the new one. Well, again, this type of picture can help us. Now, at the beginning, when we go to implement a data warehouse at the beginning, assuming that we don't have one and we're starting, you know, completely from scratch, tabula rasa, well, we might have our external sources, and our goal at the end might be to build a data mart or to build a set of OLAP cubes from the data mart. And so the first question might be, well, can't you just take data from your different data sources? And again, we had 4 or 5 data sources here at least in this process. Can we take data from those data sources, and can't we just build a cube or an analytic database directly out of it? Well, you You could try, but it probably would cause a lot of pain as you go along. There's some tried and true methodologies for ways to get at that end result. Typically, what we need to do is take the data from those external data sources, which are coming in at different grains, different time periods, and put them in what we call a staging area. And that staging area is just simply some SQL database that's a holding pattern where we can shape the data, where we can have phases where we can ultimately shape the data, where we can, and then ultimately push it into our data warehouse or our data marts or where we ultimately want to put it. So the ETL processes here to take data from our sources and put them into a staging area are going to be considerable. Now we might also have, taking a look at the other side of the world for the business users, rules for what rows a user can see. We might even have authorization tables that define that certain users can only see certain accounts or certain products or certain markets or whatever. And those rules are going to be critical. Probably some of the most acrimonious reactions I've seen from business users over the years have not come. You would think that when users or bosses get angry, it's because a job didn't run or a job had errors or wrong numbers on a report. Those are obviously not good things, but actually some of the most acrimonious results I've ever seen have been when someone was allowed to see data they weren't supposed to see, or even when there's a perception that somebody was going to be allowed to see data they weren't supposed to see. So don't overlook the authorization rules that you might need to implement. You might need to have data-driven tables that store accounts or products that define how users, what data users can see. So don't discount that extremely important aspect of data warehousing. Now, as I said several times, the components of a data warehouse are fact and dimension tables. Fact tables contain the measures that we want to roll up, and then foreign key pointers to our dimensions. And the dimensions, loosely speaking, are the master tables from OLTP systems that contain the business context. Now, as far as what fact tables might look at, I'll get to an example as far as some numbers and some columns in just a second. But our fact dimension models are going to look something along these lines. This is the world. This is the model that we want to follow for any type of data warehouse, data mart that we look to populate. Now, in the Kimball methodology, kind of taking a step backwards, the Kimball methodology talks about, they use terms like value chain and they use terms like bus matrix, and you may wonder, how does that tie to actual fact tables? Well, the Kimball methodology actually takes a step back and looks at not fact tables as a starting point, but business processes. For instance, we have retail sales, and we have retail inventory, and we have warehouse deliveries. Well, within each one of these, there might be one business activity, or there might be multiple activities we want to measure. So retail sales might be one fact table, or it could be 2 or 3 fact tables. It's going to depend upon the granularity of the data involved. So in some environments, we might take a look at this type of a value chain, and the relationship with fact tables might be 1-to-1. In other cases, it might be 1-to-many. One particular process here might contain multiple fact tables. But ultimately, we want to build something like this. We refer to this as a bus matrix. It's almost like seats on a bus, where some of them are filled, reflecting the relationships between the data, and some of them are empty, where there's simply no relationship. So, one thing to keep in mind, again, stressing again and again, we want to shape our data using ETL processes into star schema fact dimension structures using surrogate keys. So the ideal fact tables should only contain numeric numbers. I say ideal, there can be some exceptions, I'll get to them in a little while. So things like dollars, units sold, as 2 examples, and then the foreign key integer values that relate to the business dimensions. Now, for people who have been using SQL Server 2012 and 2014, we have some good news here, and that's the fact that some of the database engine features in 2012 and 2014, like the column store index, which uses X velocity under the hood, can really optimize fact structures in particular. So again, if you're using 2012 and 2014, we can really optimize fact tables by implementing column store indexes. Now, I'm going to talk about the types of fact tables here. Now, the most common is what we call cumulative transactional fact tables. hard to give an actual percentage, but the large percent of fact tables that we have are what we call cumulative transactional. Now, these are characterized by numbers that we can roll up across all related dimensions. So a typical sales table, where we can roll up dollars sold and units sold by product, by customer, and or by date. There's no restrictions in how we can roll. We can roll up by any one of the related dimensions. Now, a budget table or a goal table or a threshold table might also be cumulative transactional. A budget table might be at a much higher level, like a region or product group, but we can still roll up the spending or the budgeted volume, which is simply this data is going to be smaller. So there's typically no rules as far as how we can aggregate data here. We can sum up data by any of the related dimensions. Now, an example. Actual example of a fact table. We might have a fact table for sales for a book publisher. I did a database for a book publisher many years ago, and so we might have sales dollars and sales quantity, books sold by state, by customer, by date, by sales type, and by the instance of the book price. This was kind of a summarized fact table. Some fact tables are going to be down to transaction grain, and some of them are going to be higher. Now, there's one big rule about a fact table. Actually, many big rules, but here's another big one. All the measures here have to have or should have consistent granularity. There shouldn't be a specific rule for sales quantity to roll up that's different than sales dollars here. So the implication here, the assumption is that sales dollars and sales quantity, we can roll them up, either one or both, by state, by customer, by date, or by any attribute related to those. The transaction grain for all the measures in this fact table should be the same. Now, the T-SQL merge statement can be used to populate these fact tables. I'm going to talk about the merge statement in a little bit more detail in just a few minutes. But one thing to keep in mind is that we might very often use the T-SQL merge statement to read from our transaction data to populate these fact tables. Matter of fact, in my webcast area, back on my website, I did a webinar back on my webcast area on column star indexes back in early 2013 if you want to refer to that. So again, column star indexes can really be used in 2012 and 2014 in the Enterprise Edition to optimize fact tables. Now, I mentioned factless fact tables. This is a variation on a cumulative transactional fact table. A factless fact table is when we have no measures. What we're interested in is the tally where the dimensions come together to form an event. So if we have applicants for who are going to apply for a class or students in a class, we might have a fact table where we have a date, a course, and a sales rep or a professor or some type of foreign key, where we want to roll up the number of instances where something happens. And again, you might not necessarily think of that as glamorous, but in some environments it might be extremely critical. We might have factless fact tables for visit counts. For instance, here's an example of a factless fact table by visit type, by physician group, and by year, where all we're looking to do is roll up the number. So again, from an analytic standpoint, this can be just as critical as rolling up dollars. Now again, the factless fact table won't have any columns in it. It might have nothing more than maybe an identity column and then the foreign key pointers to all the different dimensions where we want to do tallies by any combination of patient or visit date or visit type or physician group or whatever. Well, then we have another type of fact table known as a periodic snapshot fact table. These are different. These you'll see sometimes. Here are some examples, and here's why they differ from your cumulative transactional fact tables. Probably everyone out there has a checking account or a savings account or multiple bank accounts. Well, think of the statement that you get at the end of the month. You get a statement at the end of November saying your starting balance was, so let's make up a number, $1,000, and your ending balance was $1,500. And then in December, you get another statement saying your starting balance is $1,500 and your ending balance is $1,800. Well, you wouldn't sum those numbers over a period of time. You wouldn't sum the fact you had one balance at the end of November and one balance at the end of December because the number wouldn't make any sense. those numbers represented a snapshot, a point in time, in this case a balance. This is what we refer to as a periodic snapshot fact table. We're taking some point in time count or balance or analytic value that has some meaning to us. So we might have a fact table of customer, account, date, starting balance, and ending balance. Now, we might want to average that starting balance, then ending balance over a period of time. We might want to sum it across all customers for one date to see what we have in the bank across all customers, but we certainly wouldn't roll it up across all the available measures. We refer to the measures in here as semi-additive. They can be rolled up or maybe averaged part of the way, but not the entire way. Another example is inventory. We might take inventory of product at the end of the month, and then next month and the month after that. Well, you certainly wouldn't roll up the quantity on hand, but you might average it out over a period of time. And another example might be resident counts. Many years ago, I worked in the Women, Infants, and Children, the WIC program. Well, in the WIC program, there are tallies that are taken, or counts that are taken by county or by health district or whatever, of the number of adults and infants and children on the program. Well, again, you might average them over time, but you wouldn't sum them across everything because, once again, the numbers wouldn't make any sense. This is what we refer to as periodic snapshot fact tables. So we might have special ETL processes at the end of the quarter, end of the month, end of some period to populate these. They're used for reporting, maybe to average data, but not to roll data across all related dimensions. All right, now we're going to take a look at dimension tables. Now, some dimensions are simply common across almost every data warehouse. Almost every data warehouse is going to have a date dimension. Most data warehouses will have a product or a service dimension, and most data warehouses will have a customer or a patient or some type of account dimension. Well, within these three, there are a lot of different patterns that we'll see that can certainly apply to other dimensions. First of all, most dimensions are going to have the following pieces of information. They're going to have an identity column, some type of surrogate integer key that's assigned by the system. So in SQL Server, the identity, or possibly in 2014, a sequence object as the primary key. And then we might have a business key. So in the case of a product dimension, a product SKU, or in the case of a customer dimension, a customer number. And then maybe one or more descriptions, maybe a short description and maybe a long description for reporting, and then different attributes that describe each particular row that reflect the different types of entities by which people might want to roll up data. So in a product dimension, people might want to roll up sales by group, or by subgroup, or by brand, or by color, or by size. Now, some of these are going to come together to form hierarchies. For instance, subgroups might roll up into groups, which might roll up into brands. On the customer side, we might have multiple hierarchies. I use as a classic example a Kroger in downtown Atlanta. That might roll up to the city of Atlanta, to the state of Georgia, into the region of the Southeast, and then to the United States as a whole. But that Kroger might roll up to a Kroger corporate grouping, which might in turn roll up to a division. So we might have multiple hierarchies within a customer dimension. Now, there might also be ranges of values, and here's something to take into account with certain types of information we might have a business dimension. We might have 5,000 products in a product dimension, and there might be 4,900 distinct weights. So if we did a select distinct of all the weights in a product dimension, out of 5,000 products, we might have 4,900 distinct weights. Well, the question is, do we want to carry those 4,900 in the business dimension in the data warehouse, or do we want to store some analytic range of values? For instance, the fact that one product weighs 6 ounces, the other weighs 6.5 ounces or whatever, do we care about the difference there? Well, that's up to the business. Maybe it is. Maybe we're dealing with precious items or precious metals or something like that, where that small difference could be very, very important. Other times we might just simply care about ranges, like anything from 1 ounce to 10 ounces and 11 ounces to 20 ounces or whatever. So we might store the entire list of discrete values, or we might store a range of values. If you want to impress your friends and your coworkers with the fancy 50-cent term, There's a 50-cent term that's used to describe taking a large list of values and building a much shorter list, and it's called discretization. If you work in analysis services, you might know that there's a capability analysis services to build discretized bucket counts. But whether you brought analysis services to do it or whether you have the business do it, that's something to keep in mind. Now, on the date dimension side, we might have a script that creates a date dimension because we might want to roll up data by week, by month, by quarter, by year, by fiscal year versus calendar year. So we might have multiple types of date hierarchies in here. Two of the things to take into account with some date dimensions. What I'm about to describe is not terribly common, but it can happen. We might need to store data by time. So, for instance, we might be dealing with cash register data that's coming in, and we want to report on sales by every cash register in 15-minute intervals. We might have a time dimension as well with every different interval throughout the day, and an identifier that we might store in the fact table as a foreign key. We might also have to deal with seasonality. Now, if you're wondering what seasonality is, the biggest example I've ever had to deal with is seasonality. I used to work with the company that made Mrs. Paul's fish sticks. It used to be Vandy Camp Foods. Now it's someone else. Well, they were very interested in sales during the weeks of Lent up to Easter. Well, you know anything about Easter and Lent weeks, you know that Easter is a different time period every year, which means that the weeks of Lent are a different time every year. Sometimes Lent might start earlier or later in February, or go later into April. It all depends upon the year. Well, suppose we want to take a look at sales in Lent week 1 across years. Well, because Lent starts at different time periods, we might need to store in our date dimension columns to identify what we call seasonality, whether it's the Lent week or if we're looking to track sales for the proverbial day after Thanksgiving, which might occur at a different time period of year. We might have identifiers in the date dimension there. Now, date dimensions are usually going to look something like this, where we have all the different attributes that represent the different ways we want to roll up data, and then some type of primary key that's tied to the fact table. Now, notice how this date PK, this identifier column, is actually in year-month day format. Whereas in something like a customer or product dimension, the primary key is usually going to be the dumb surrogate integer. Many times in date dimensions, people will restructure the primary key in year-month day format to help DBAs when they're maybe partitioning data. So that's one exception where we might have an identifier with some intelligence built into it. Okay. By the way, I realize I'm coming up on 6 o'clock. If I can, Julie, if I can have maybe about 15 more minutes, I can wrap up in 15 minutes. Obviously, if anybody needs to drop off, I understand that. But if I can have about 10 or 15 more minutes, the last part should go pretty quickly. If I can have just a little bit more time, if that's okay.
Yeah, that's fine. No worries.
Okay. Okay, appreciate it.
Thanks.
Now, some rules about populating populating dimensions in fact tables. We always populate dimensions first. Well, if we go back a couple of slides to one of our diagrams here, well, it makes sense. If the fact tables contain foreign keys that refer back to our dimensions, obviously we need to populate new data in our dimensions before we can populate data into our fact tables. So we populate dimensions first and then fact tables second. And again, the T-SQL merge is really going to be helpful for both fact and dimensions. Now, I mentioned that on my website I've got several different downloads. I want to briefly call attention to one. If I go back to my website, I've got another download here called Transact SQL for Developers, and one of the examples in this slide deck and in the code samples actually walks through the merge capability. I don't have time to get into merge in any specifics right now, but if you want to know more about how to use the T-SQL merge, highly recommend learning this, because merge really comes into play as part of a pattern for populating both facts and dimensions. One of the nice things about merge is that it's a combination of an insert and an update in one DML statement, and we can actually take the results of inserts and updates and output it to other tables that we might use as the basis of what we populate into fact dimension tables. So sometimes we might use merge to target directly into fact dimension tables, Or we might be using these to populate operational tables where the output of what actually got added or what got changed becomes the delta that's going to be turned around and used to populate data warehouse tables themselves. So merge can play a variety of different roles in populating fact dimension tables. Now, in many instances, we want to build what we call star schemas, which are denormalized structures. So coming back just a minute to my example of a product dimension. A product might have a corresponding subgroup and group and brand, and customers might have a corresponding market and region and zone. We really want to denormalize them into one flat table per business grouping. Sometimes you might see dimensions more normalized, and we call that a Snowflake schema. Now, I'm not going to say that Snowflake schemas are terrible, they certainly aren't, but I usually, as a general recommendation, I recommend using star schemas as a starting point and only utilizing Snowflake schemas if there's some specific reason for doing so. Sometimes Snowflake schemas can complicate certain ETL processes like processing type 2 changing dimensions. And it can also complicate end users who are trying to build reports against a Snowflake model. So as a general rule, you want to try to build star schemas unless there's some compelling reason to do otherwise. And I'll come to a compelling reason in just a minute. There's one exception where a Snowflake structure might make sense. All right, I mentioned role-playing dimensions, so up to number 7 here, role-playing dimensions. Again, this is not a complicated topic, but it's one that we typically see in many data warehouses. A common example is one dealing with dates. We might have an order table where we might, on an order, have an order date, the due date, and then when it's supposed to ship. Well, we might want to roll up order dollars or freight or any other metric by the order date definition or the due date definition. So our fact dimension structure might have multiple primary key, foreign key relationships so that users at the end of the day can look at data by any one of those. I one time had a client that had 6 roles where a particular dimension key serves 6 different purposes in a fact table. So it's certainly not uncommon to have these in a data warehouse. Now, I'm going to get into some specifics of, as far as how this might be implemented in the different analytic tools that are available to us. Some people might be using analysis services tabular model that came about in SQL Server 2012. Well, it's worth mentioning that that the tabular model in analysis services actually has a limitation. Even if you have 3 primary key, foreign key relationships supporting a role-playing structure, something like SSA is tabular only supports one active relationship. It won't, out of the box, let a user roll up order dollars by any of those 3 date definitions. You're going to have to supplement it with DAX formulas for the other calculations you might have, or you could simply create 3 views of the date dimension, 1 for each role if you wanted to. Now, something like analysis services OLAP, still to this day one of my personal favorite products, actually implements that out of the box. If we give an OLAP cube a fact dimension relationship with a role-playing definition, the analysis services OLAP definition engine will actually build multiple roles for us out of the box. So another example here, we might have an account that serves as an invoice account or a purchase order account. So that's another example of a role-playing relationship. Now Services OLAP will actually support that out of the box. All right, another type of relationship we might have is what's referred to as a junk dimension. Now this one almost has a negative connotation, but it really doesn't. This is not exactly the most critical type of relationship, but it's one that can help. Let's say that for an order table, we might have a corresponding order type and an order status and an order payment code and an order category code and maybe other codes like this. We have a lot of codes tied to orders where the codes don't really have any relationship between them. So order type doesn't necessarily tie to order status and it doesn't tie to order payment. Well, we might have an order type dimension and an order status dimension, an order payment dimension, where all we have in there is just the primary key and the description, and the primary key is used as a foreign key in the fact table. Well, some people might observe that that might result in a sort of a mild proliferation of dimension tables where each one is kind of small. Well, there's Nothing wrong with that, but here's another pattern that you can implement. You can basically take all of these, what some people might call junk dimensions, and place them into one, essentially a Cartesian product, a self-join of all the combinations, and have one primary key that's associated with each possible combination, store that in the fact table. Certainly that's going to make the fact table simpler. Instead of 4 or 5 or however many foreign keys in here, we're going to have one. And we simply have a Cartesian product for all the possible combinations within the dimension. There's no absolute rule over this. It's more of a judgment call when you want to implement this, but it is a pattern to consider when you have this type of data. All right, now I mentioned, moving on here, I mentioned that there might be one example of a Snowflake schema where we have dimension tables related to each other to form a picture, and we want to take this one into account. Let's say that we have a customer dimension where we have hundreds of thousands or millions of customers, and each customer might belong to a county where we have a large number of attributes that are tied not to the person but to the county. So we might have 100,000 people who live in the same county. Well, instead of storing all of the attributes associated with a county in one big, fat, flat customer dimension, we might have what we call an outrigger dimension, where we have attributes that are tied to the parent county. And this is to keep from having to store what is essentially a large number of values that are not going to vary. In other words, we have a cardinality issue where we have a low cardinality number of values within the customer dimension across many customers within a single county. So if you have this type of a pattern where you have a parent definition, and the parent definition itself has a large number of attributes that are not going to vary across individual customers, we might want to consider storing them in a separate table. Certainly going to be helpful if the demographics change every X number of years. This is not terribly common, but it can happen. All right. Now the next topic here is one that we could spend an entire hour on. Actually, the next two topics we spend an entire hour on. And it is what we call many-to-many bridge relationships. This is a scenario where we are trying to relate data from one fact table to a dimension, but we need another table containing relationships with another dimension table to form the entire picture. And here's a couple of examples. Let me hop over to the SQL Management Studio here for just a second. I mentioned the book publisher world. Here's an example. In the book publisher world, we might have an author who has written multiple books. So we've got author 411 here. Author 411 for one book was involved in writing half a book, and on another book, the author wrote the whole book. So notice the author share here. So an author can write multiple books. Well, this book 232, we take a look at it. Book 232 was written by that author 411 and also by another author. So coming back to the slide deck here, we have a case where a book can be written by multiple authors who each contribute a percent, and an author can write multiple books. Well, we might want to calculate sales, not by book, but by author, for purposes of calculating royalty. So for instance, if I am involved in just 10% of a book, and we want to determine my royalty, we don't take the sales for the entire book. We take it based upon my share of it. My share is stored in another bridge table. Well, if we want to relate sales by book, or excuse me, we want to relate sales by author, we need to have that bridge table where that bridge table has a pointer to the book and also to the author. Well, let's remember that pattern for a minute because I'm going to go to a second example, one dealing with AdventureWorks, the AdventureWorks demo database, and with currency conversions. So coming over here to AdventureWorks. In AdventureWorks, the sales, the core sales is by the US dollar. But we've got multiple currencies in here. And I'm looking at two here, the Canadian dollar and the US dollar. There's certainly other ones in here as well. Well, those currencies also have currency rates for each particular day. So if I want to know the sales for any one currency on a particular day, I need the help of a bridge table, which is tied not just to the currency, but to each individual day. Let's come back to the first one here. Same pattern, just simply different data. We wanted to take a look at sales by a dimension which seems to be way out in the distance. We need some bridge table which has that dimension in common as well as one other common dimension, in this case books. So we start to see a little bit of a pattern here. Let's take a third example. A while ago I was talking about the food industry and the fact that some people might deal in units and some people might deal in cases and some people might deal in pounds. Well, we might store shipments by pound, but we might want to take a look at them by case or by consumer unit or maybe by pallet. Well, the unit to measure conversion might be different by product. For instance, one particular product group, the conversion factor between pounds to cases might be such and such, and between pounds to units might be such and such. So if we want to take a look at shipments by some other unit of measure, we're going to need help of a bridge table which has that unit of measure in common along with one other dimension in common. So when we have this scenario where the relationship that we ultimately want to report on between a metric and a business dimension, where there's no direct relationship, it involves multiple entries across another dimension, we might need some type of a bridge table in order to basically complete the analytic path. Not a common scenario, but it's one that can happen. Now, I mentioned analysis services tabular and OLAP a minute ago. The thing to keep in mind is that SSA is tabular. This is another thing that it doesn't support out of the box. So if we actually had a scenario of book sales that we wanted to look at by author, we need to actually put in some DAX code to implement that to sum the sales of the book and then utilize the relationship across the related dimension. Something like analysis services OLAP is going to be able to handle that one out of the box. It actually has capability to be able to deal with bridge tables and get the relationship natively. All right, just a couple of minutes remaining here. Item number 11 here, and this is again one that we could spend an entire hour and a half on, and that's what we call type 2 changing dimensions. The scenario with a type 2 changing dimension is, I'm going to whittle it down to a simple example here. Once again, dealing with the book world, with the book publisher world, let's say that we had a book that was published on such and such a date and its price of $59.95. And then many years later, the same book, or it could be any kind of a product, has a price change. It's now $64.95. And we want to track sales, and not just sales but returns, when the book was under the old price and had the old PK versus the new one. Well, there are many things that we need to keep in mind. First of all, we need to model in the database the fact that the granularity here of this particular dimension is not going to be the book title. It's going to be the instance of the price. We want to preserve history here, so that's something to keep into account with the model. The other thing we need to take into account is writing out the correct, into the fact table, the correct book PK at the time of the sale. So coming back here to my data, any sales that take place before January the 1st of 2008, we want to write out to the fact table under the old book price PK. Any sales that occur January 1 or afterwards, we want to write out the book price PK based upon what was in effect at that time. So the ETL process needs to read the sale date, dive into here based upon what price was in effect at that time to write out the right record. Now I've got some notes in here on what we need to do to retire the old row when we have a book price change in the dimension, and what we need to do in the fact table as far as writing out the correct record so that we can have the correct historical reporting and be able to point to the right instance of the book price. There is something else to keep in mind here, and I've got some notes in the slide deck, and that's what happens if we get late arriving data. What happens if we were supposed to get a price change on October 1, but we didn't get it until November 1? That means that for 30-some days we were writing out what was essentially the wrong book PK, except we didn't know it. So what happens in that case? Well, you might possibly say, okay, you write some type of an update process to correct the data. Well, maybe, maybe not. Key point here. Sometimes the word update can be almost like a 4-letter word to a fact table. In some maybe regulated industries, we might not be able to update data in a fact table. In that case, we might need to post reversing entries. Yes, it does actually happen. It's usually where we have accounting implications, but we might possibly need to write out rows of the fact table to reverse the quantity or the sales based on the old PK and then write out the new one. So that's something to keep in mind when we get late arriving data, is that we might need to issue corrections or possibly write out reversing entries to fact table data. Something to keep in mind. Now, how you would implement that, again, it's a topic we could spend an entire hour and a half on, but we'll at least keep in mind that this kind of thing can happen. Now, options for implementing type 2 changing dimensions. Well, you could write pure T-SQL code in your ETL to retire the old row and insert the new one. You could write custom SSIS packages with custom T-SQL code. You could use the SSIS slowly changing dimension transformation, where you actually provide the information for what column represents the column where we want to retain this, preserve the historical changes, and it actually generates an entire pipeline workflow for you. It works pretty well. Performance-wise, it tends not to be all that fast, and it's also not very flexible. If you actually if you alter the generated workflow and then go back and change some of the parameters, it's going to overwrite your changes. Anybody who's worked with a slowly changed dimension who could probably attest to that. There are some free open source alternatives with benefits that are out there. Now, a separate note, if you want to know more about how you might implement a type 2 changing dimension, I mentioned in a prior lifetime I used to actually teach this, and I actually have a couple hours of evidence from a course I taught. We'll actually walk through an example of a type 2 change in dimension. So in the slide deck that's on my website, I've got a link here to another link within my site that actually has a 3-part download, an entire video download, if you want to walk through an example of a type 2 change in dimension. It's actually a couple hours long, definitely worth it. All right, 2 items here, and then I'm done, and they're quick ones. Some 2 definite no-nos with fact tables. First of all, storing nulls in fact tables. Generally not a good idea. Here's an example. Let's say that we have a fact table with sales and we have a cost center. And maybe 95% of that time the cost center is populated and maybe 5% it's not applicable. Well, what some people might do here on the left is they might implement a fact sales table with the cost center foreign key tied to the cost center dimension. And for rows where the cost center isn't applicable, we store a null. Not recommended. And the Kimball methodology talks about this as well. Not recommended. One of the reasons is it makes it a little bit difficult for people to report on the roll-up of sales where there was no cost center. Here's a better approach over here on the right. What we might do in our dimension is store some dummy value, like a -999 or a -1. And if you wonder how can you do that in an identity column, well, you can set identity insert on in that dimension table. Insert a dummy value there, and then set identity insert back off. And then for those instances, store the -1. So your ETL has to have some logic to know what that value is, however you wind up implementing it. You might have another flag in the dimension table to recognize, to identify that undefined member. Well, this way, it's just simply another dimension entity, just like all the other ones, and users can roll up the sales amount much more easily. So, as a general rule, not a good idea to store nulls in for foreign keys in fact tables. Much better off utilizing this approach over here on the right. Okay, last item on here. Storing ratios in fact tables. Not a good idea. As an example, very simple example. Let's say that we are trying to calculate return percentages, and we have 2 stores. In store A, for a month, we have $10 in returns and $20 in sales, so we didn't have a lot of sales. Store B, $10 in returns, $100 in sales. Well, if we actually tried to store the percentages in the fact table, how would you aggregate them? The return percent for the one store is 50%, the return percent for the other store is 10%. What's the point in rolling up those numbers? It's self-evidently ridiculous. There's no way that you could get to a roll-up number that would make any sense. Here's what you want to do. You basically want to store, obviously, the returns and the sales. But then, because we want to have some type of a weighted return percent, what we want to do is store the numbers that represent the numerator and the denominator and then calculate the return percent on the fly. So as a general rule, any calculation that comes about as a result of division, any percent, any ratio, it's really best not to store it in the fact table unless you need to at the lowest level for record-keeping purposes. But certainly when you roll it up, you're not going to want to roll up that percent in any way. You're going to want to take the numbers that are involved in the ratio, roll them up, and then calculate a weighted percent on the fly. I actually had an example the other day, as amazed as I was. Saw an example. I was troubleshooting a new client data warehouse. Troubleshooting example where percentages on a report were actually rolling up. We're actually summing up percentages. So in this example, their data was showing a 60%. Obviously, that number makes absolutely no sense. So definitely don't want to do it that way. Okay, we have reached the end here. I want to throw two other quick book recommendations for anybody who knows anything about the SQL BI world. You probably recognize and definitely would recommend these authors. Chris Webb, Alberto Ferrari, and Marco Russo have written two fantastic books for both the tabular model as well as analysis services OLAP. Their 2012 analysis services tabular book is fantastic. They also wrote a very, very good book, actually the best book on OLAP cubes that are out there several years ago. They have a new version for 2012 as well that you can find on Amazon. Same authors, so I definitely recommend reading them as well as the Kimball book. So, well, appreciate everybody hanging around. I see we still have 117 attendees here, so for people on the East Coast, I realize that cut into dinner time, so appreciate everybody hanging around. Again, hopefully you can see the value in the slide deck. There's a lot of information in here. It goes way beyond the presentation here. Again, the slide deck is up on my website. Let me get my website back up here. It is just simply www.kevinsgoff.net. So let me get it back up here. Just go to the download area of my website, and it's the on my download page. It is the second download here. So that's the slide deck. And again, feel free to check out my webcast at any downloads. So.
Okay.
Well, I'm ready for dinner. I'm ready for dinner myself.
No problem. Thank you so much for that excellent presentation, Kevin. I think we do have a couple of questions here, but I think it might be best if they were forwarded to you so that you can address them on your website, if that's okay.
Sure. Any questions? Yeah, I'll address my website, and any email. Anyone who emails me as well, certainly reply by email. So.
Okay.
Appreciate everybody attending, and thank you very much for having me.
Yes, thank you, Kevin. So, guys, if you're still around, we do have a survey that will be pushed out very shortly. Please fill that in, and you'll be entered into a chance to win a $25 Amazon gift card. So, thank you so much. Have a good morning, afternoon, evening, wherever you are. Thanks. Bye.
Okay. So long, everybody.